Hi class, this is Dr. O'Connor, and in this video I'm going to talk briefly about mixtures, and then we're going to get on to scientific measurement, things like the metric system, scientific notation, rules for significant figures, and so on. So let's go ahead and start with mixtures. So what is a mixture? It's actually a blend of pure substances. So it could be two or many more pure substances. So for example, the shampoo that you use to wash your hair, that is a mixture. A chocolate chip cookie is a mixture. A glass of iced tea, with or without the ice, is a mixture. So mixtures can be homogeneous or heterogeneous. A homogeneous mixture is uniform throughout. For example, if you have a glass of iced tea without the ice, that would be a homogeneous mixture. A heterogeneous mixture is not uniform throughout. So that iced tea with ice cubes would be a heterogeneous mixture. A chocolate chip cookie would be a heterogeneous mixture. Another example of a homogeneous mixture would be when you take sugar and you dissolve it in water and you stir it up and it's all dissolved. That would be a homogeneous mixture. So we can come up with examples of both homogeneous and heterogeneous mixtures. Okay, Italian salad dressing is definitely a heterogeneous mixture. It's difficult, for example, if you had a salt water solution where the salt is completely dissolved, it's difficult to determine if that is just water or if it is a homogeneous mixture of water and salt. So we can usually distinguish heterogeneous mixtures though, because again, they're not uniform throughout. Think of that delicious chocolate chip cookie. We see the cookie base, and there are chocolate chips embedded. That is a heterogeneous mixtures. As far as mixtures go, the components of a mixture can be separated. So components of a mixture can be separated by physical means. Sorry about this. For some reason, when I write with this pen using the PowerPoint, I have a hard time controlling it. So components of a mixture can be separated by physical means. The mixture can vary in composition. So in other words, you could have a very sweet sugar water mixture, or add less sugar and it's going to be less sweet. So these are the two most important properties of a mixture. Components can be separated by physical means, and the components can, or the mixture can vary in composition. So next, we need to talk about units and how we measure physical quantities in the lab. So a physical quantity, that's a property that can be measured. We can measure height, mass, volume, density, conductivity, all sorts of things that we can measure. When we measure these things, we have a number and we have a unit. A number means nothing without a unit. If I say that the size of that book is 5, that could mean anything. It could be 5 inches, 5 centimeters, what have you. So we use units. In chemistry, we use either what we call SI units, standard units of measurement, and these are defined by an international system of units. And we basically use the metric system. Let me see if I can stop this silly thing. Good. So, usually in the US, we measure mass in pounds or ounces, but in the metric system, we measure mass in grams, milligrams, micrograms, kilograms, what have you. So the International System of Units, or SI units, these are a set of units that scientists all over the world have agreed to use when we report physical quantities. So here are some SI and metric units and their equivalents. So for mass, the SI unit is the kilogram. So if I'm publishing a paper and about some scientific study or research that I've done, for mass, I will always use the kilogram. For meter, for length, I use the meter. For volume, the cubic meter. Temperature is Kelvin. Time is seconds. The metric unit for mass is the gram, and that's what I use in the lab. But if I were writing a paper, I would need to convert that to kilograms so that I have SI units reported. In the lab, we use meters, liters for volume, degrees Celsius for temperature, because I have to measure the temperature using a centigrade scale or thermometer. And again, time is in seconds. And then some of the equivalents here. A kilogram is 1,000 grams, and that's equivalent to 2.205 grams. A meter is 3.28 feet, and so on. So other units are derived from SI units. For example, speed is, here it's miles per hour, but in the metric system, it's meters per second. That's using SI units. Okay. Density is grams per cubic centimeters. So we use the metric base unit of a meter and then modify that with a prefix. Okay. So this table just shows some base units in the metric system. Length is meter, volume is the liter, mass is the gram. And what we do is we modify these base units using these prefixes. And yes, you need to know all of these prefixes, their symbols, and their equivalents. So mega is a capital M, and that means that's the base unit. So let's say megameters, that would be 1 million megameters. Okay, so make sure you know these prefixes and make sure that you're able to convert between these metric units. We're going to talk about significant figures, and in the lab we're always taking measurements. So basically we will, I might measure the side of a table and it's 25 inches wide, right? So what we do is we have to measure something according to the measuring device we use. So I have to use a certain number of digits. So significant figures are the number of meaningful digits used to express a value. So that means all of the digits that we know for certain, and the last digit is always an estimate, and it's usually uncertain by plus or minus 1. So for example, if I have 64, if I report 64.12 centimeters, that is a length that is between 64.11 centimeters and 64.13 centimeters. So the uncertainty in that is plus or minus 100th of a centimeter. The uncertainty is in this last digit. That's in any measurement that you're given. You still report that last digit, but even when you report a mass from a balance, for example, let's say I weigh something that's 5.26 grams, you report this last digit, but the uncertainty is plus or minus 100th of a gram. Okay? We use exponential notation, or scientific notation. That's a number that is expressed as the product of a number between 1 and 10 raised to some power. Okay? So we'll show how to do that in a second here. So if we have 12 grams of carbon, I'm telling you, it contains this many carbon atoms. Well, you don't want to keep writing this over and over again. That's a large number, a lot of zeros to include. So I write this then in exponential notation. Remember, this number has an implied decimal point at the end, or after the last zero. So what I do is I move this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So that would be written as 6.02 times 10 to the 23 atoms. And so in the case where you're dealing with a decimal, you would move the decimal point from left to right. And in this case, I would move from left to right all the way here. So that would be 1.99 times 10. And because I'm moving the decimal point from left to right, that'd be a negative 23 grams. Now, let's take a look at this graduated cylinder to determine the number of milliliters of water. So the first thing I do is I see that each gradation here is 1, 2, 3, 4, 5 milliliter, or 1 milliliter. So each gradation is 1 milliliter. So here, I like this representation better. I can see it good. So I know for sure I have 15, 16. I know for sure I have 17 milliliters. So I have 17 milliliters. I have to estimate between the gradations. So I'm going to estimate that as 17.6 milliliters. You might look at it and say it's 17.5 milliliters. Somebody else might look at it and say it's 17.8 milliliters. All three are correct. We know for sure there are 17. This last digit is an estimate. Now we're going to talk about rules for significant figures. You know, many times when you're doing calculations with significant figures, your calculator will give you an answer something like this. Okay, so you've got all these digits. You can't always report all these digits. You're only allowed to report the number of digits that show the precision and accuracy of your measuring device. Okay? So, significant figures, knowing how many significant figures are in a measurement is very important. So, here are the rules. You need to know these rules. All non-zero digits are significant. So that means this number here contains 4 significant figures. This one here contains 1, 2, 3, 4, 5, 6, 7 significant figures. The only time there's some questions are when zeros are involved. Anytime you have zeros between 2 non-zero digits, those zeros are significant. So we would count this as 3 significant figures. This would be 4. This one here would be 1, 2, 3, 4, 5, 6, 7. Okay? Zeros at the beginning of a number are not significant. They're just placeholders. So this measurement here would have one significant figure. This one here would have three significant figures. Now be careful. We have zeros in front of the number here. Those are not significant, but this 0 is between two non-zero digits. It's significant. So this number here has 4 significant figures. This one here has 3. Zeros at the end of a number and after the decimal point are significant. So this 0 is significant. So this measurement has 5 significant figures. Here, this is a leading 0. It is not significant. Both these zeros, this 0 is between two non-zero digits. This one is at the end of the number after the decimal point. It is significant. So this measurement has 4 significant figures. This one has 3. This one has 4. Now, you might see something like this. Anytime you see the decimal point after a number that ends in zeros, that means all of the zeros are significant. So here we would have 3 significant figures. Zeros at the end of a number and before an implied decimal point may or may not be significant. We don't know. We would need more information here. So all I can say for sure is that this one has 2 significant figures. This one has 2 significant figures. What I can do is I could use exponential notation to remove any ambiguity. So 65,000, if that was 2 significant figures, I would report it as 6.5 times 10 to the 1, 2, 3, 4. Okay, if it was 3 significant figures, that could be 6.50 times 10 to the 4. Okay, exact numbers are not significant. So, or I should say they don't affect the final result when you do calculations using significant figures. So counting numbers, for example, there are 10 books, 11 students. Those do not affect the result. Conversion units, those are exact. So 1 gram is equal to 1,000 milligrams. 1 pound is 16 ounces. Those do not affect the final result. Addition and subtraction, some rules. When you're adding and subtracting measurements, here are the rules. The answer cannot have any more, and here I should just put digits. So let's change that to digits. Cannot have any more digits after the decimal point than either of the original numbers. So I'm adding these two, and this one has 2 digits after the decimal point. This one 4. My answer can only have 2 digits after the decimal point. So that would be 58.06. Here we're doing a subtraction. Here there are 4 digits after the decimal point, 3 after this one. My answer can only have 3 digits after the decimal point. So this would be my answer. Some rules for rounding. If the number, so for example, if I need to round 2.643 to 3 significant figures, if the number that remains is, or if the number that you're dropping is less than 5, you don't do anything. This would round to 2.64. If it's greater than 5, so 2.647, so I want to drop this, I round up. That'll be 2.63. Okay. Another way to do that, if the number you're dropping is exactly 5, what you do is look at the digit that remains. If it's even, you keep it. If it's 2.6435, if it's odd, you round up. You don't have to do this, but that's what you would do if you were working with a lot of data. Basically, a lot of people just, if the digit they're going to drop is a 5, they just round up the last remaining digit by 1. And even Excel does that, so that is fine. Now, when you are in multiplication and division, there's a different rule. The answer cannot have any more significant figures than the measurement with the least number of significant figures. Here we have 4, here we have 2. I'm multiplying them. My answer can have no more than 2 significant figures. So this would be the answer. Same with the division. Here I have 4, here I have 7 significant figures. My answer can have no more than 4 sig figs. That would be the answer. When you're doing multiple operations with significant figures, so for example, this one here, I keep track as I go. So I have 2.976 minus 0.07246. And my calculator gives me this answer, 2.90354. And I know that my answer, because I'm subtracting, can have no more than 3 digits after the decimal point. So I underline it just to show. I don't round until I finish the whole calculation. So that is going to be divided by 1.41. Okay, so we divide that by 1.41. So this here would have 4 significant figures. This would have 3 significant figures. Because I'm dividing, my answer could have no more than 3 significant figures for this problem. So my answer would be 2.06. So let's take a look at some definitions here. Mass. We define that as a measure of the amount of matter in an object. Now, weight is actually the measure of the gravitational pull on an object. So mass and weight are two completely different things. So for example, if I have an object that I weigh here on Earth, okay, its weight is going to be less on the moon because of the gravitational pull, okay? So the mass, though, of that object should be the same on both the moon and on Earth. So mass, unlike weight, is not dependent on location. Weight is dependent on location. So what we do is we determine the mass by comparing the mass of the object to the mass of a reference mass. So that means if I determine the mass that way, the mass of the object will be the same on Mars, Earth, the moon, or wherever. The base unit for mass in the lab is the gram, and we can modify that using prefixes. You need to know these equivalences here, okay? So 1,000 grams is a kilogram, a milligram is 1,000th of a gram, 1,000 milligrams is a gram. One English to metric conversion that I know, it's the only one I know, but if I know this, I can convert anything. 1 pound is 454 grams. We measure length and distance in the lab in the metric system, and that's the meter. In the lab, in the chemistry lab, meter is usually pretty large, so we're usually measuring millimeters and centimeters, okay? So here are some different conversions. Here's a very different one. When you see an A with a degree symbol above it, this is called an angstrom. Uh-oh. Oh, no. Okay, there we go. I thought this froze up. That's an angstrom, and it's equal to 10 to the negative 10 meters. We used to measure bond lengths in angstroms, okay? Here's a very useful unit conversion. 1 inch is 2.54 centimeters. We work in nanometers. It's a billionth of a meter. Here we have a meter is 100 centimeters, as 1,000 millimeters. 39.37 inches. Again, you want to know these conversions. I will hold you responsible for converting between units. Volume, the amount of space occupied by an object. The SI unit for volume is the cubic meter. In the lab, we use the liter, and we modify it with the prefix milli for milliliter. So 1 liter is 1,000th of a cubic meter, and that's equal to 1 cubic decimeter. 1,000 milliliters is a liter. 1,000th of a liter is 1 milliliter. So we normally call a milliliter a cubic centimeter or a cc. Okay, they're all one and the same. One good conversion from metric to our system is 1 gallon is 3.8 or 3.78 liters. This is a nice little drawing from your book, and this shows a cube that has 1 meter sides, and you divide this cube into 1,000 parts, and we can see that a cubic meter is 1,000 cubic decimeters, and 1 cubic decimeter is 1,000 cubic meters, which is equal to 1 liter. So this is a very useful conversion right here. Make sure you know that. Okay, this table, this is just some conversions between English and metric system. And here I show temperature scales. Obviously in this country we use the Fahrenheit scale. In the chemistry lab we use degrees Celsius and also a Kelvin temperature. Okay, so these are the formulas for each of these temperatures when we need to convert. And I'm going to give you an easier formula for Fahrenheit because you're going to have to use these. Degrees Fahrenheit, 9/5 is 1.8. So 1.8 degrees Celsius plus 32. And degrees Celsius then would be the Fahrenheit degree minus 32, all divided by 1.8. Kelvin temperature, that's usually used for gases, and Kelvin is equal to the degrees in Celsius plus 273. So at 0 K, that's equal to what we call absolute zero, and that is equivalent to a negative 273.15 degrees Celsius. There are no negative Kelvin temperatures. Also, when we report a Kelvin temperature, so 312 Kelvin, we don't use the degree symbol. Okay, I will say you can tell from the image here that the Celsius degree and the Kelvin unit are the same size. Okay, the Fahrenheit degree, though, differs in size from Celsius and Kelvin units. So here's a problem. What is the Fahrenheit temperature equivalent to 57 degrees? What is this temperature in Kelvin? The Kelvin we can do right away. Kelvin is the degrees Celsius plus, plus 273. And that's actually 0.15. So 57 plus 273.15, that's 330 Kelvin. So let's go ahead and convert this temperature to Fahrenheit. So Fahrenheit is 1.8 degrees Celsius plus 32, and that's 1.8 times 57 degrees Celsius plus 32, and that equals, that's 1.8 times 57 plus 32, that's 134 1.6 degrees Fahrenheit. Okay, I'm going to wrap this video up, and I have some videos for a little bit later, both on working with conversion factors, how to set up conversion factors, and then energy and heat. Everybody have a great day, and take care. Bye-bye.